All right, so we'll just get to the script language at this point. That was sort of an overview of how the GUI works and how you can use it. The next section talks about the flexibility and the definition of the scripting interface. So the scripting is based on MATLAB or Octave if you're familiar with Octave. They both use, so not exactly the same, but you'll be familiar with GMAT scripting if you're familiar with MATLAB or Octave scripting. Okay, so single line statements with line continuations, case sensitive, loosely typed. This means you can assign a string to the number 1 and it'll convert things for you automatically. Beginning and ending statements for blocks, while and end while instead of brackets and braces. And resources are created before they're used. So you can't just assign x equals 1. You have to declare x as a variable, create my variable x, then assign x equals 1 and use it as such. So one thing that's different from other sorts of scripting is we're divided into 2 sections. Because we're using the scripting to map directly to the graphical interface, we have this concept of initialization, the resources tree, and the mission sequence, which is sequential. So the script we've divided into 2 sections, an initialization part and a mission sequence part. And the dividing line between those two is this begin mission sequence command. Initialization maps to the resources tree. It includes static assignment only. You can't use variables or arrays or math in that section. The mission sequence assigns to the mission tree. This allows manipulation of existing resources, but you cannot create new ones. Okay? So an artifact of the concept of initialization and execution is that you can create your objects at the top of the script and you can use them in the bottom. You can't create them in the bottom. You can't create new things while you're manipulating existing things. There's this division there. So this is the simplest possible script you can have, really. What we're doing here is creating a spacecraft called SAT. You've seen this. We're setting the SMA equal to the number 7,000. So this syntax looks a lot like MATLAB structure syntax or any kind of object reference syntax. Number 7,000. Here we're creating a report file called R. So this create is a built-in statement that's used for creating things. Spacecraft and report file are the names of resources. And once you create something with a name, you can then reference it. So here we're saying the file name of R is a string myreport.txt, and we have single quotes there. And now we have our begin mission sequence command that divides the two. And we have our one command, report R, and here's a call to a parameter. What's the 7 major axis of my spacecraft? And we have a label here. Okay. So as shown, all this stuff will link when you load it in the GUI. There's your satellite. Here's your report file. And here's your command. And notice that the name of the command in the GUI is the name you've given it in the string here in the command statement. So I mentioned math syntax is like MATLAB. It's actually identical to MATLAB to the extent it can be. We actually test it by writing tons and tons of equations in MATLAB, evaluating them to get the answer, and copying them over to GMAT scripts and running them identically and making sure the numbers match. So when I say based on MATLAB, everything's identical to MATLAB. We have some additional extra little functions here. Operators are as you would expect, built-in functions. Everything is matrix aware. You can multiply arrays together and it'll perform matrix multiplication, same as MATLAB. One thing to note when I say using math, math is allowed only in the context of assignment statements. So I can say variable x equals 1 plus 2, or my variable equals 24 times 60 squared, number of seconds in a day. I can't do this right now, just because, you know, GMAT was designed to do mission simulation and not be a full-fledged programming language. Right now, you can't do like y minus z in the context of a while command. Instead, you would say, you know, my test equals y minus z, and then while x is less than, you know, my variable. So that's one thing to be aware of. So here's just an example of using math in an actual case. You can copy and paste this into a script if you want to. But here's my spacecraft. I'm assigning the SMA of it. And then I'm creating some variables. Period, mu, pi. I assign mu to the Earth's value of mu. And then I can calculate pi, arc cosine -1. And I can use those variables to calculate the period, the Keplerian period of my orbit using the SMA of the spacecraft that I just set. All right, so that's a pretty simple example. All right, now jumping back to parameters now. I mentioned parameters. Well, this one has an example of a parameter. So this, let me just restate that this here is a parameter. It's calculating the value of SMA at that time. So if I had propagated for a day, that value would be different because it's retrieving that value at the time that it's called. So parameters can have two types of dependencies. Central body, so like SMA has a central body parameter. You can say some major axis with respect to the Earth or respect to Mars or an asteroid or whatever, or with respect to another spacecraft if you wanted to. Or it could have a coordinate system dependency. For example, let's see, inclination has a coordinate system dependency. You can calculate inclination with respect to J2000 or ecliptic inertial or any other type of coordinate system you want. Or it can have neither. If you ask for the time, what's the epoch of the spacecraft, that it doesn't make sense for that to have a dependency. You just say, what's my epoch, and it returns it. Like I said, they're calculated on the fly. And here's a key point, as I obscure it with my drawing. If omitted, a default dependency is used. So I can write spacecraft.x without the Mars fixed in there. If I do that, it's going to fill in that dependency with a default value. Sometimes that's convenient, sometimes it can be a problem. So here's an example. So I'm going to use the same script in several things, several slides. So here's our spacecraft. We're setting the coordinate system to Mars fixed, creating a report file. And in our mission sequence, we're just reporting spacecraft.x and spacecraft.beta angle. Okay, so this is the x is the Cartesian, the x component of the Cartesian state of the spacecraft. Beta angle is, someone remind me, I think it's the angle between the spacecraft and the sun for some definition.
Spacecraft orbit and sun.
Spacecraft orbit, okay, orbit normal. Yeah. So if you type that, it's going to fill in default dependencies for these values. Okay. So if you leave out the dependency on x, it'll fill in Earth J2000, which normally is a pretty good assumption. If you leave out the beta angle central body, it'll fill in Earth. Again, a reasonable assumption.
Are the defaults in the documentation?
They should be. If they're not, it's because they're all Earth J2000 or Earth. We might just have it in a sentence above the table of parameters instead of on each one. Yeah. Actually, yeah, because I wrote it. Yeah, it's in there. All right, so here we've changed the script a little bit. Now we're setting things. So here we're setting right ascension to 90, eccentricity to 0.2. Now look at our spacecraft. We've defined it in terms of the Mars fixed coordinate system. So if my spacecraft is defined as Mars fixed, and I set my eccentricity, you probably want the eccentricity set in the Mars fixed coordinate system. It's setting the value for the current configuration of the spacecraft, which is usually a good idea. So here, it's setting the right ascension in terms of Mars fixed, and it's setting the eccentricity in terms of Mars. All well and good so far. Now, here I'm going to set the field using a parameter. So I have an equation. I'm setting the eccentricity to 2 times the current value of eccentricity. So basically, I'm taking my spacecraft, doubling the eccentricity of it, and I'm going to use that from now on. Well, here's the problem. It looks at this part. This is assigning a parameter. Where's my pen? Assigning a parameter. It fills in Earth. Here I'm setting the value on the current value of spacecraft. I'm setting it. It fills in Mars. I've just taken my hyperbolic Earth eccentricity, doubled it, and set it to my Mars orbit. Not good. So the key point here is always, unless you're absolutely sure and you know the rules of this, which you probably won't after the end of this class, but it'll take some time, you always want to state your dependency. Because GMAT independently will do what you probably want done here, and it'll do what you probably want done here, but put them together and it's doing something very bad. So the way around this is always state your dependency and you'll avoid the situation. Or if you use the graphical interface, it'll fill all that in for you. You don't have to worry about it. Okay, moving on. So I mentioned control flow statements. There's if else, while, for. That's conditional. While, these are just typical definitions. For is a certain number of times. While is till a condition is true. So an example of if. So I'm saying if altitude is less than 300, do a maneuver. If it's not, then continue onward. So this is a station keeping sort of construct where you propagate until you've decayed to a certain point and then you want to bump it back up. A while loop. So here I'm saying just keep burning until my fuel mass gets down to 5 kilograms and then stop. And a for loop. Here I'm just saying here's my variable I. This is like MATLAB. Loop from 1 to 50 in steps of 1. So this will just do something. It'll loop 50 times, essentially. Solvers we'll get into in lots of detail later. I'll just mention there's 2 types of solvers, a targeting and an optimizing. They're similar to loops in that they iterate. So they iterate and change the value of different parameters until a certain condition is achieved. And they contain certain statements that control the flow of that. So target, you can vary things and achieve other things. Optimize, you can vary things according to constraints, and you can declare a minimization objective function. We'll go into all that stuff later. So that's sort of a tour of the script. Now, one of our questions earlier was, how do you manage going back and forth between the graphical interface and the scripting interface? There's different benefits to either. Setting up graphics and stuff is usually done in the graphical interface. You can just run it and see the results. Setting up complex calculations, you usually want to write that in a script language. So what we typically do is we go back and forth. I'll do some things in the GUI, edit some things in the script, go back and forth like that. So we have this concept called the synchronization between the two modes. So we have a built-in script editor. It includes some nice features, which is why you might want to use it. But there's some issues to be aware of. I'll just demonstrate some of that. All right, so here's my script. This was created in the GUI, I think. Here's the script representation of it, opened in the script editor. So there's things like, here's a sync button. This will save your script, sync it with the rest of the program. This will do the same thing and run it. And here's some just classic save buttons. But what you want to look at is this, or sorry, not that. You want to look at this at the top, synchronization status. Okay, so right now the synchronization status of this is that it's synchronized because I loaded it from a file. I haven't made any changes, so everything is good. Now, what if I rename a spacecraft? I want to name leader to leader A. Now I have a yellow saying my script has been modified. Which is okay. It just means you have to click the sync button down there. Everything will sync up. It'll go back to synchronized mode. Okay. Now, what if I then go into my script and I change my SMA to 7,000. All right, now you have a red saying I've made changes to my script, I've made changes to my GUI. They're not identical anymore, you're unsynchronized. And the way to get that back is you have to pick which one you're going to save. So I'm either going to save my changes to the script file, or I'm going to save the changes that I did in the interactive interface, graphical interface. So you either click Save for the script, or Save in the GUI, and it'll ask you, it'll warn you, this is going to overwrite the other representation. Once you do that, it'll go back to a synchronized status, and you're good. So just something to be aware of. It's completely possible to edit your script in an entirely different editor. I use Vim or Notepad++ or something like that. You don't have to worry about that situation in that case. But a lot of people like using the built-in editor. Just be aware of this synchronization issue. So that's sort of on the topic of best practices. One thing I always like to remind people is keep your script minimal. If you write it by hand, keep it minimal. If you create a bunch of stuff in the GUI, click Save, it's going to write out everything that it needs to know to recreate that mission, which means it's going to write out the values of all of its parameters. Your script will be 1,000 lines long, which is okay. But if you expect to work in the script language as a programming language, you want to keep things smaller than that. So the key point to realize here is that missing settings will just go to their default values. So you only need to write the lines that are changes from the default configuration. Okay. Use the Show Script button. I'll actually demonstrate that. Let's say I've configured a very complex but very cool orbit view configuration here that I want to save for later. Okay, I'm looking at the Show Script button right here. I click that on every panel, and it shows me a dump of the script language that will recreate that object for you, which is pretty nice. If you're working in the script mode, you want to configure something real quick, copy the block of script, paste it into your own editor. It enables that sort of workflow. It also is a handy way of just figuring out what the default settings for everything is, or what fields are named, or what sort of data type, can be used there. I'll repeat it again. Always explicitly state parameter dependencies. And I have here do as I say, not as I do. On the slides, there's limited space, so I had to compress things a little bit. But you may find yourself getting into trouble if you rely on default settings in terms of parameter dependencies, unless you know what you're doing. Number 4, use script event to encapsulate complex algorithms. Let's show an example of that. I'm going to load the lcross script again. All right, so here's the mission sequence. It's not too bad. It has maybe, 20, 25 commands associated with it. But you'll notice one of the commands here is called initializations. I'm looking right here, initializations. And that has this symbol that says this is a script, what we call a script event, which means if I open up initializations, here it contains another 90 lines of scripting code. Okay? So the way we did that is we surrounded that block of scripting with this statement here called begin script. And then if I go at the end, there'll be an end script also. So what that does, if I comment it out, I'm just going to comment out begin script and end script. Okay, save it and sync it. Now my mission sequence is full of these equation commands that don't mean anything to me. Now it's horribly long and complex. I can't see my actual mission because of all the commands. What it's doing is every distinct command in the script gets assigned a node in the mission tree. That's how it's a one-to-one mapping there. The way to get around that is I can write, I can surround a complex bit of calculation or initialization list or something like that in these begin script and end script commands. And now everything's collapsed into one node with a friendly name. I can go into it and I can operate it. I can operate with it in terms of a block of scripting. So that's pretty handy. So that's my best practice. Use script event statements to encapsulate complex algorithms. And finally, label your commands. So you noticed in the previous script the commands weren't labeled, so they had friendly names like report1 and report2 and propagate1. You can actually label your commands using this string syntax here, and they'll show up with names that actually make sense to you. All right. Let me load this script just because it's interesting. This example shows a little bit of the power of the scripting infrastructure. So let me run it so we can look at it. What this is doing is it's putting a spacecraft around Earth Moon L1. And the thing about orbiting Earth Moon L1 or any of the libration points is that you can't just put a spacecraft there and expect to orbit for years and years without maneuvers. Those libration points are unstable, and you're not in a three-body only environment anyway, so you have all these other perturbations. So as you orbit that libration point, you're going to, it's such a sensitive environment that unless you correct, you're going to fly off into heliocentric space, probably. So the way missions handle this is they propagate for 6 months, they perform a maneuver at when they cross a plane, looks like when they cross the XZ plane here. And they perform a correction that will allow them to continue orbiting for the other 6 months. And then they do that every 6 months, okay? It's called libration point station keeping. And this script implements that for, I think, 7 revolutions. So you can see the green line here. That's the targeter trying to apply different maneuvers to achieve the condition of staying in that orbit. Oops. Okay, so there's pretty complex stuff going on. There's multi-body dynamics. There's propagating to a plane crossing and doing some targeting to figure out what do I need to do to stay in that orbit. But that whole thing is done with that mission sequence. 1, 2, 3, 4, 5, 6, 7, 8 commands. If I open up the script, this is it. That's the entirety of it. Here's my for loop. Here's a target sequence. Target sequence. Here I'm varying my velocity direction maneuver, perform a maneuver, propagate to a plane crossing, y = 0, and then achieve a velocity component, in this case Vx = 0. So is this a simplified example? Sure, but 7 commands to do 7 revs of libration point station keeping. It's sort of illustrative that combine a scripting interface with some control flow and some automatic targeting sequences, and you can do pretty powerful stuff and not a lot of lines of script. All right. By way of wrap up, this is just some notes on other things you might want to do with GMAT, a little more advanced. This is the GMAT folder structure. If you actually go into your GMAT folder on your desktop, you'll see this structure. Say you want to configure things. The bin folder here contains a startup file that's how you enable and disable different plugins. If you want to do change or add gravity models, you would go to the gravity folder. If you want to change your EOP file, you go to the planetary coefficients folder. Leap second files in the time folder. Here's our documentation. Math specs, user guide. They're all in this docs folder. If you generate output files like ephemeris files and report files, they'll end up in this output folder by default, unless you specify some other location. And the samples folder is something worth exploring. We have about 40 different example scripts in there from various missions and various showing off different functionality and things. So if you have a question about how to do something in particular, likely there's a sample mission that does part of it. You can just copy and use. I mentioned plugins. GMAT ships with several default plugins. It has an interface where you can write plugins in C++. You can compile them against GMAT, and you can distribute them separately from the actual tool. So there's several default ones built in. 2 of them are disabled by default. The ones that link to MATLAB and link to the MATLAB optimizer. We just disable it because not everybody has MATLAB and it needs some special configuration anyway. That configuration documentation is in the user guide under the MATLAB interface chapter. It gives you a description of how to configure that. You can enable or disable plugins through the startup file, and we have several alpha level ones available. So for example, here's my GMAT folder. Plugins are located in this aptly named plugins folder, and here's the list of them, the ones that we ship. For local users, your proprietary folder will have some additional ones. For external users, it'll be empty. And the way to manage that is I'm going into the bin folder. There's this file called GMAT startup file. Double click that, and there's a well-commented file that has a section here for plugins. All right, so here's all the default ones that are enabled. Notice these 2 are commented out. That's your MATLAB and your fmincon. If you want to enable those, just comment them, uncomment them, turn them back on. Here's some alpha ones that are all commented out. If you want to use these, talk to me or send us an email or something with your description of what you want to do. These can be useful, but they're alpha for a reason. They're not fully tested. You have to work within some limitations, but we distribute them anyway. And then we have a section for internal-only plugins. For external users, these will be commented out. These include MarsGram, some drag models, and the internal optimizer. All right, in terms of getting help, there's a couple ways to do it. First of all, if you have a question about, for example, well, let me do something simple. An impulsive burn. So here's the impulsive burn panel. Lets you configure coordinate systems and delta V vectors and things. There's this help button right here on all the panels. If you click that, you'll get this handy help page that has descriptions of all the fields. So data type, allowed values, whether it's settable or gettable, meaning is it a field that you can set or a parameter that you can calculate, what the default value is, what the unit is, and if it's accessible in the GUI or the script. So that was a question before. And some of these, I picked one that happened to be deprecated. It'll have a note there saying this field is deprecated, don't use it in new scripts. So that's we have a description, some links to other resources, description of the fields, description of the GUI, and then some discussion and examples down here at the bottom. So that's the field-specific help. You can also click the help button here, and you'll come to our home page, and you can read the entire user guide, get the tutorials, etc. There's a note about our web page here. We build the user guide nightly with all kinds of new updates and fixes and things. We post it online. You can go to that web page and get the latest copy. And another note that we have a wiki here. That's our home page. It's pretty useful. We have user forums you can post to. And we have 2 mailing lists, one for users, one for developers. Just open, you can ask questions, we respond to them. Another one that is not mentioned here is GMAT info. So you can go to this web page to see all of our lists. GMAT info is one that I recommend everybody subscribe to, because that is things like release announcements, and we sent announcements for this training to that list, and announcements of beta programs and whatever else. So that's a good one. So this is probably a good time to take some questions. We've just gone through a lot of material about how different parts of GMAT work and the various interfaces and things that that can be used.
Internally, how do we get the internal version of GMAT?
There will be an announcement going out that has details like that, and the short answer is that it's on internal network share, and you can go to it and grab that. I will give that to you after the class, or I'll send an email. I'll send an email to participants of the class, essentially saying, when you want to grab GMAT, here's where to get it.
For this documentation now, is that going to be available? We can grab that somewhere online?
Yes. You mean the slides?
Yeah.
Yeah. So that, yep, we're going to post all that stuff.
Okay.
Yep. If you, you could email yourself a copy of that. Well, it's kind of big.
It's big.
Yeah, it's big. So if you have a government flash drive, you can do that way.
Joe, is there documentation on any of these plugins that you kind
of? So, yeah, the question was, is there documentation on the plugins? The documentation for the features in the plugins are all in the normal user guide. What's not sometimes clear is which plugin enables which features. So that, yeah. Sometimes it's obvious, like libMATLAB interface, does the MATLAB interface. But yeah, everything, if you know the features that you're trying to enable with a plugin, all that documentation is built into the normal user guide.
Okay.
And we should say on the page if this is a plugin feature or not. That would be helpful. I'm not sure if we went through that or not. Oh, you know what? I have a better answer. No, I don't. Yeah, so this page for the MATLAB interface should say somewhere that it's a plugin. Yeah. All right, so at this point, I have in the agenda that sort of a self-guided tutorial. So Rizwan, can you help me out?